Yeah, good morning to you all. So to whole experiments videos we have shared. Now the next experiment, fifth one is Fourier transform, finding Fourier transform of a arbitrary signal x of t. Okay. So here Fourier transform already we have studied. Basically it changes time domain signal into frequency domain, right? X of t has been changed to x of omega, where the formula for x of omega is this one, whatever I have written here, right? So x of omega equal to x of t, my input signal multiplied with e power minus j omega t dt. So we can implement this integration in MATLAB, or we are also having a direct keyword is there in our MATLAB software, that is FFT, fast Fourier transform. This is completely related to digital signal processing subject, but for continuous time domain we are discussing now. So for finding Fourier transform of a continuous time signal, we are also having one more keyword, Fourier. Fourier. This is a keyword we are having in MATLAB software to find the Fourier transform of a continuous time signal. So we are not going to implement this integration formula. You have to do the theoretical calculations for whatever input signal we are taking for this particular inbuilt command Fourier. Okay, just to Fourier of for which signal you want to find in transform, that you need to mention under Fourier inbuilt function. Okay. Yeah. So here in our program, I'm going to take input signal as this one. Okay. This x of t equal to e power minus 80. Okay. And further, this x of t, I'm multiplying with u of t. Okay. So now I'm going to take my input signal as minus a into t into multiplied with unit step signal u of t. So for this particular u of t, there is a keyword for generation of this is this one, and that keyword is heavy side. Heavy side is a keyword to generate a unit step signal. Heavy side of x or heavy side of t variable. Heavy side of x means u of x function will be generated. Heavy side of t means t function will be generated. But I'm not going to use t variable in our program because some toolboxes will be there based on t variable and all. That is the reason instead of t, I'm going to use exp of minus a into x. Okay, u of x, like that. Instead of t variable, I'm going to use x variable. Okay. So that is a change you can observe in the program. So just one thing you remember, I'm going to give input as this one. I'm going to give input in the program as exp of minus a into x into u of x. First, I'm going to generate this exponential. After that, I'll be multiplying with unit step. This total rectangular box, whatever input is there, that I'm going to give as input to this inbuilt function Fourier. Okay, this is a theoretical part related to Fourier transform. And after this, after finding Fourier transform x of omega, whatever x of omega is there, from this I'm going to sketch its a magnitude spectrum as well as its a phase spectrum. Both the things we need to plot, that we will be seeing in the programming part. Okay, magnitude spectrum and phase spectrum. Okay, this is a background theory related to Fourier transform. Now let us go for a programming part. Let me share the screen of a program. Yeah, here is a program, simple program only. CLC, clear all, close all, these three things. As I already said, it is a common for all the programs. Symbol of X. First time that it indicates that I'm going to generate a function or signal in terms of variable X. Instead of t, as I said, instead of t, I'm going to take here X variable. So, okay, SYMS, this is a keyword. If you want to know in detail about this, just in command window, you need to type help space SYMS. You will get complete details about that inbuilt function. Okay. So, SYMS is a keyword. It indicates it generates a variable, whatever you write here. Okay. Now, X is a variable. A equal to symbol of 0.25. It's the same as, a equal to 0.25 only, like that. So I'm assigning 0.25 to a variable a. Next, f equal to input, give exponential signal as input. That means here we need to give the input. What is the input I have to give? Small f as exp of minus a into x is a variable. This I have to type in the command window, exp of. Next, as I already said, the same function f is multiplied with, that means now exp of minus a into x is multiplied with heavy side of x. Heavy side of x. So here now f is going to be exp of minus a into x again into u of x. U of x. Okay. This is my input signal like e power minus 80 into u of t. For this, you have to do the theoretical calculations also. E power minus 80 u of t, whatever Fourier transform will be there in theory part, same thing you have to get in the program also. So now capital F, observe here, capital F is Fourier keyword I am using. Fourier of this total input signal. F equal to exp of minus ax into u, this total input signal. Okay. So that transformer signal will be now in capital F. So I have to separate its magnitude and phase now. So a variable I have declared a equal to absolute of capital F means magnitude spectrum. This is for magnitude. Magnitude. Okay. Next, EZ plot. EZ plot means randomly it will take frequencies on x-axis and magnitude values on y-axis. So random plot, randomly taking values on x-axis means we need to use EZ plot. Okay. X label frequency in radians, Y label magnitude. Figure. And now I am going to create one more figure window for phase response. Okay. These instructions are for phase response. P equal to angle of this transformer signal capital F. Again EZ plot of P. Phase is going to be in radians on y-axis. On an x-axis, frequency will be there. Again on x-axis, frequency in radians. Just a title I have written. Here I didn't write the title. Now you write the title also like it is magnitude response. And here you can write x label as frequency in radians, y label as phase in radians. Okay. So random radians, it is frequency in radians I have written. Frequency. Okay, let us see by running it. Just to frequency in hertz will be there, not in radians. If it is radians means omega we call. Okay, omega we are plotting now, so it will be in radians only. Okay. This is all about the program. X label frequency in radians, Y label magnitude. And here phase also same, X label frequency in radians, Y label phase in radians. That is phase response. Okay. This is a program. So let us save it and run. Okay. Now once you click on the run, in command window, it is asking a equal to 1 by 4. We have given give exponential signal as input. So here we need to give exp of minus a into x. Just to press enter. So we got the x equations here. Small f is exp of minus 0.25 into x, nothing but x by 4 into heavy side of x means u of t. It's like e power minus 8t into u of t, where a is 1 by 4. Now capital F means 1 by a plus j omega. 1 by a is 1 by 4, j means I, omega is omega. Absolute of this one is magnitude response, P equal to phase of this. Okay, this expression you need to verify theoretically. For this particular input, small f, this is a capital F output, you need to verify theoretically. Let me show the responses also. So you can see here. Let me show the responses. So here it is a phase response. Okay, phase is odd symmetric will be there. Phase by reverse will be there. Phase response. Like in the same manner we will be having. Just let me once again run it. Once again I am running to show the outputs to you all. Exp of minus a into x. So we got all the output waveforms. To show the outputs, I am stopping the share. Yeah, this is a magnitude response, which is a even symmetric. Okay, even symmetric. Even symmetric. Magnitude response is always even symmetric. Frequency in radians, magnitude here. Generally, we can convert it into dB also. Okay, magnitude response. Let me show the frequency phase response also. Phase response is always odd symmetric. Okay, whatever part is there, that will be reflecting here. Whatever part is there, that is reflecting here. That is a property of odd symmetry. So this is all about phase response and magnitude response. Okay, this expression, whatever capital F is there, 1 by A plus J omega. A is 1 by 4 omega. This capital F, you need to do the theoretical calculations. So this is all about Fourier transform. Many applications, spectrum analysis in communication, we use this Fourier transform. Okay. In FFT, about the keyword FFT, you will be studying in detail in your digital signal processing subject. Here we have used Fourier as a keyword to find Fourier transform. Okay. Thank you.